As the world rejoices over the all-clear signal for 3 Atlas, history's third deep space voyager, a more concerning development is stealthily unfolding, and it has only just come to our attention. A comet, exhibiting dramatic outbursts, is venturing alarmingly close to Earth's orbital path. It evaded our detection until the Sun itself inadvertently revealed its presence, and on October 20th, 2025, a mere 8 days from now, it will achieve its closest proximity to our planet. What implications does this hold for us here on Earth? Is this the genuine peril? Remain with me until the conclusion, and you will grasp why the true danger was never the celestial body dominating the headlines, but rather the one we almost overlooked entirely. If these enigmas have captivated you as profoundly as they have me, be sure to click like and subscribe to ensure you don't miss a single update as this unfolding narrative progresses in real time. Share your location, the current time there, and your thoughts on whether we're receiving the complete truth regarding these paradigm-shifting discoveries in the comments section below. And if you wish to contribute to the growth of this community, please share this video across X, Facebook, Reddit, or even within your personal group chats. Your support is the very reason we can continue to pursue stories of this magnitude. Therefore, thank you for standing by us. Part 1. The diversionary spectacle. Right now, the entire world is abuzz with news of 3 Atlas. The media proclaims it a mystery. Social platforms are flooded with speculation, while astronomers work diligently to assure us of its harmlessness. And they are correct. 3 Atlas, that celestial wanderer originating from beyond our immediate solar vicinity, will safely traverse Earth's vicinity at a considerable distance of 1.8 astronomical units, equating to approximately 167 million kilometers. NASA has stated this unequivocally. No threat. Its orbit will remain distant, a cosmic tourist gliding past before vanishing back into the vastness. So, what fuels our fascination with it? It's the fact that it originates from elsewhere. The very word interstellar possesses a captivating allure, causing us to overlook practical considerations. We are drawn to the exotic visitor, the stranger at our door, yet we fail to acknowledge who might already be within our home. While the world's attention is fixed on 3 Atlas, another entity is surreptitiously entering our cosmic neighborhood. Comet C-2025R2, designated SWAN after the instrument responsible for its discovery, is rapidly approaching. On October 20th, 2025, just 8 days from now, it will reach its closest point to Earth. Not 1.8 astronomical units, not even one. It will be 0.2606 astronomical units, approximately 39 million kilometers. This is far closer than one might initially assume. It is closer than we are comfortable with for any uninvited guest. Allow me to elaborate on the nature of this object. R2 was first identified in late September 2025 by an amateur astronomer named Vladimir Bezugi. He was not using a traditional telescope, but was analyzing data from a solar wind instrument aboard the SOHO spacecraft. His focus was on the ultraviolet emissions of glowing hydrogen. This is an unconventional method for comet detection. Typically, ground-based optical surveys scan the heavens, pinpointing faint points of reflected sunlight. However, R2 remained invisible to these instruments. It had been concealed within the sun's blinding glare, too close in angular proximity for earthbound telescopes to discern. This phenomenon is known as the Hulek or Huli blind spot effect. Objects within this zone are effectively phantoms, existing but imperceptible until they emerge from obscurity. R2 became visible only after it had already passed its perihelion its closest point to the Sun on September 12, 2025. By the time it was detected, it was already en route towards us. Its perihelion distance was approximately 0.5 astronomical units, about 75 million kilometers from the Sun. This proximity is sufficient to vaporize volatile compounds from its surface, triggering outbursts and potentially destabilizing its structure. And indeed, it did. In late September, observers documented a sudden surge in brightness. The comet's magnitude increased significantly to around 5.9 or 5.6, depending on the report. Its coma, the diffuse cloud of gas and dust enveloping the nucleus, expanded dramatically. Photographs revealed a distinct greenish halo, a characteristic signature of diatomic carbon and cyanogen radicals fluorescing under solar ultraviolet radiation. Its tail stretched across several degrees of the sky, visible through binoculars if one knew precisely where to direct their gaze. However, here lies the crucial point. We still do not know the size of its nucleus. We are unaware of its rotational state. We cannot ascertain if it is fractured or if it is poised to do so. Comets are inherently unpredictable bodies. They can shed fragments, disintegrate into multiple pieces, and disperse debris fields along their orbital paths. Should R2 undergo any such event, these fragments will deviate slightly from the parent object's trajectory. They will spread out, forming a dispersed cloud of potential intersection points with Earth's orbital path. The minimum orbit intersection distance, or MOD, between R2 and Earth is approximately 0.048 astronomical units. This translates to roughly 7 million kilometers. In cosmic terms, this is an infinitesimal separation. It represents the boundary between safety and potential peril, contingent upon subsequent developments. Now, I am not here to assert that R2 is destined to impact Earth. Current orbital projections indicate this is unlikely. However, I am here to highlight that our prior inability to detect it constitutes the actual risk. We have developed a detection system that functions admirably for celestial objects situated in the correct celestial positions, exhibiting appropriate brightness and appearing at opportune moments. Yet, if an object remains hidden within the sun's glare, arrives from an unexpected vector, or experiences a sudden brightening after we have ceased observing, we miss it. We overlooked R2 until it was practically upon us. How many other such objects have we missed entirely? This is not an endeavor to incite panic. Panic is unproductive. This is about fostering an awareness of that which consistently evades our observation. It is about recognizing that the most alarming celestial bodies are not those making headlines, but rather those we fail to perceive until it is far too late. 3 Atlas serves as a distraction, a magician's flourish designed to divert attention while the genuine trick unfolds elsewhere. R2 is the actual trick. Therefore, here is our course of action. Initially, we will dissect the 3 Atlas diversion, demonstrating its inherent safety. Subsequently, we will delve into all that we know and all that remains unknown about R2. We will examine speculative risk scenarios, the dust trails, the fragments, and the meteoroid swarms. We will draw parallels to past near misses that we barely perceived, objects that slipped past our defenses with mere days or hours of warning. Finally, we will address what you should monitor, what you should demand from the institutions entrusted with tracking these phenomena, and the consequences that arise when our detection systems falter, for they do fail more frequently than one might imagine. And when they do, the entity that slips through is not always the one you were anticipating. Part 2. The Mechanics of Discovery. Why did SWAN detect it, while ground-based surveys did not? Comets are typically identified through optical sky surveys. Telescopes meticulously scan the night sky, searching for faint points of light that shift their position against the backdrop of stars. These points brighten as they approach the sun, their icy composition sublimating and forming tails. This method has been employed for centuries and is generally reliable, except when it fails. Comet C 2025R2 was not discovered using an optical telescope. Its discovery was made by a hydrogen emission detector situated aboard a spacecraft orbiting the Sun. This instrument is named SWAN, an acronym for Solar Wind Anisotropes, and it is part of the SOHO mission, the Solar and Heliospheric Observatory, launched in 1995. SWAN was engineered to image the solar wind by detecting hydrogen L-alpha emissions within the ultraviolet spectrum. Hydrogen emits light at a specific wavelength, 1.6 nanometers, which is invisible to the human eye, but prominent in ultraviolet radiation. When comets release water vapor through sublimation, this vapor dissociates into hydrogen and oxygen. The hydrogen then disperses, forming an extensive cloud surrounding the comet, significantly larger than its visible coma. SWAN is capable of observing this cloud from millions of kilometers away, even when optical telescopes detect nothing. This is not an entirely novel technique. SOHO SWAN has been instrumental in discovering thousands of comets throughout its operational lifespan. The majority of these are small, sun-grazing objects that plummet into the solar atmosphere and vaporize. However, R2 is not a sun grazer. It is a visitor from the outer solar system, likely originating from the Oort cloud, making a close pass by the sun before returning to the outer reaches. What rendered it imperceptible to ground-based surveys was its celestial position. It was too proximate to the sun in the sky, its angular separation too minuscule. Telescopes on Earth are incapable of looking directly at the sun without sustaining damage. Consequently, there exists a zone encircling the sun, a cone of obscured vision where celestial objects effectively vanish from our sight. Astronomers refer to this as the Hulek effect or the Huli blind spot, depending on one's preference for crediting historical figures. The underlying principle remains consistent. Objects within this zone are essentially invisible. R2 traversed this zone during its perihelion passage. It completed its orbital sweep around the Sun on September 12, 2025, at a distance of approximately 0.5 astronomical units, roughly 75 million kilometers. For several weeks preceding and following this event, it remained undetectable by optical surveys. By the time it emerged from the Sun's blinding radiance, it had already passed its perihelion and was proceeding outwards, heading towards Earth's domain. It was at this juncture that Vladimir Bazugi, an amateur astronomer, identified it in the SWAN data. He was systematically examining archived ultraviolet imagery, searching for the distinctive glow of hydrogen emissions. He detected a discernible blob, a diffuse cloud that exhibited positional shifts over time. He flagged this anomaly, prompting further investigation by other observers. Optical confirmation followed, verifying the comet's existence. However, by this point, weeks of crucial observation time had been lost. We lacked any data regarding its pre-perihelion behavior. We were unaware of its brightening progression, the evolution of its orbit, or whether it had already commenced fragmentation. Detection bias operates as a stringent filter. Optical surveys are constrained by minimum magnitude thresholds, gaps in their sky coverage, meteorological interruptions, and regions obscured by glare. Hydrogen UV instruments, such as SWAN, possess distinct sensitivities and their own blind spots. While they can detect comets that elude optical telescopes, They are not designed for comprehensive sky mapping. They are specialized tools, and specialized tools are adept at identifying specialized phenomena. The repercussions of delayed detection are considerable. Orbital uncertainties are magnified when observational data is limited. Extended observation periods are essential for refining trajectories, measuring orbital perturbations, and accounting for non-gravitational forces like outgassing. R2 was identified late, rendering its orbit inherently uncertain. Even weeks later, margins of error persist. We possess a general understanding of its trajectory, but general is not synonymous with precise. In the realm of celestial mechanics, precision is paramount. Furthermore, we missed its early activity. Comets frequently experience outbursts in proximity to their perihelion when solar heating triggers explosive releases of volatile compounds. If R2 underwent such an event, we did not witness it. We are uncertain whether it shed significant fragments during this period. We do not know if its nucleus fractured. We are unaware of its rotational state, which dictates its spin and potential wobbling under asymmetric outgassing forces. All of this vital information is now irretrievably lost. We are navigating blind, attempting to predict the behavior of an object whose spectacle we only began observing midway through its performance. This situation is not attributable to individual astronomers' shortcomings. Rather, it represents a fundamental limitation of our current detection network. We have optimized our systems for specific types of celestial objects situated in particular regions of the sky. When an object deviates from these parameters, it escapes our notice, and it escapes our notice entirely until an amateur astronomer with access to sophisticated spacecraft instruments happens upon a subtle hydrogen glow within archived data. How many other comets have we failed to detect? How many are currently traversing the solar system, invisible to us because they are in the wrong place at the wrong time? We do not know. We cannot know. That is precisely the crux of the issue. In the next segment, we will examine what R2 has actually done since its discovery, focusing on the outbursts, anomalies, and structural peculiarities that elevate this comet beyond being merely another icy celestial body. Part 3. R2's observable activity. Allow me to guide you through the sequence of events. On September 11th, 2025, Vladimir Bezugi identified a source of moving hydrogen emissions within the SWAN imagery. The object was assigned the designation C2025R2, with the R signifying the latter half of the month of discovery, and the 2 indicating it was the second comet detected during that period. Optical confirmation was swift. Ground-based observers redirected their telescopes to the calculated coordinates and observed it. A nebulous patch, a coma emitting a faint glow in the pre-dawn sky. The comet had passed its perihelion the preceding day, September 12th, at a solar distance of approximately 0.50347 astronomical units. This is a close proximity. It is close enough to facilitate the sublimation of water ice, carbon dioxide, methane, and ammonia, all the volatile substances carried by comets. It is close enough to instigate significant activity, and activity did indeed occur in late September. Observers reported a sudden increase in brightness. The comet's apparent magnitude surged, with some estimations placing it at 5.9, while others reported 5.6. Given that magnitude is a logarithmic scale, even a minor numerical change represents a substantial amplification in luminosity. The coma visibly expanded. Photographs captured a distinctive greenish halo encircling the nucleus. This coloration is indicative of diatomic carbon molecules fluorescing under the influence of ultraviolet radiation. Such emissions are common in comets. Carbon compounds sublimate from the nucleus, become ionized by solar radiation, and subsequently emit green light. While it appears exotic, it is simply a chemical reaction. The comet's tail exhibited asymmetries. Certain images displayed distinct streamers, narrow jets of material emanating outwards, away from the sun. This suggests localized outgassing, likely originating from active vents on the nucleus's surface. Comets are not homogeneous bodies. They are conglomerates of ice and rock, with certain regions possessing a higher concentration of volatile materials than others. As the nucleus rotates, different vents are exposed to the sun, triggering intermittent bursts of activity. The resultant tail often displays shifting shapes, pulsates, and occasionally bifurcates into multiple streams. R2 exhibited all of these characteristics. Observers also noted a significant retention of dust. Ordinarily, solar radiation pressure propels small dust particles away from the comet, forming a smooth tail. However, if these particles are larger or possess adhesive properties, they lag behind, creating a diffuse cloud that disperses gradually. R2 appeared to be generating a considerable quantity of larger dust particles. This observation carries significant implications. The presence of large dust grains suggests that the nucleus is shedding substantial material, potentially in the form of fragments or surface pieces dislodged by thermal stress. If these fragments are sufficiently large, they could persist as independent entities, each following its own trajectory. These divergent trajectories could then create a debris field across space, extending away from the parent comet. One particularly striking image of R2 was featured on the Astronomy Picture of the Day website on September 18, 2025. It depicted the comet's greenish coma against the twilight sky, with its tail extending upwards, away from the glare of the obscured sun. The comet was still low on the horizon, presenting observational challenges, but it was unmistakably visible. Astrophotographers managed to capture it, some utilizing binoculars and others employing small telescopes. Reports describe the tail as spanning several degrees in length, resembling a spectral ribbon stretching across the celestial expanse. However, here lies a critical caveat. Predictions regarding cometary brightness are notoriously unreliable. Comets do not adhere to simple, predictable patterns. They exhibit outbursts. They diminish in brilliance. They fragment. Their luminosity is contingent upon the surface area actively undergoing sublimation, which in turn depends on the nucleus's size, composition, rotational state, and the intensity of solar heating. While we can formulate educated estimations, comets possess a penchant for surprising us. For R2, under optimal conditions, predictions suggested a magnitude of 4, rendering it readily visible to the naked eye from a location with minimal light pollution. Other forecasts were more conservative, anticipating a magnitude around 6, necessitating the use of binoculars. As of October 10, 2025, the reported magnitude is approximately 6.7, placing it just beyond naked eye visibility. Whether it will achieve greater brilliance hinges on the occurrence of further outbursts, and we currently lack the knowledge to predict this. The nucleus itself remains unresolved. Telescopes can only discern the coma, the luminous envelope of gas and dust. The solid core remains obscured within, too diminutive and faint to be distinguished. We do not know its precise size. Estimates based on its observed brightness and activity suggest a diameter on the order of a few kilometers, but this remains a conjecture. We are also unaware of its shape. We cannot determine if it comprises a single solid body or a loosely aggregated cluster of fragments. It is also uncertain whether it has already undergone fragmentation. Some comets fracture silently, shedding pieces without dramatic displays, and the evidence only becomes apparent later when high-resolution imagery reveals multiple condensations indicative of multiple nuclei. While speculative, this possibility warrants consideration. The outburst observed in late September suggests the presence of internal volatile reservoirs. Internal pressure likely built up within the comet, culminating in a violent release. This could be due to the sublimation of carbon monoxide ice, which can cause explosive expansion, or it could stem from subsurface pockets of water ice suddenly exposed to solar radiation. Alternatively, it might be a consequence of structural failure, a fissure opening and venting gas. Regardless of the precise cause, this event occurred once, and it could recur. And if it happens at a critical juncture, when the comet is in close proximity to Earth, the resulting fragments will disperse to form a debris cloud, a cloud that we might potentially traverse. Next, we will transition to the quantitative data, the precise orbital parameters, the distances, velocities, and geometric configurations that delineate the difference between mere scientific curiosity and genuine concern. Part 4. Concrete figures and an orbital reality assessment. Allow me to present the geometric details. Comet C-2025-R2 traces an orbital path around the Sun on a trajectory that is nearly parabolic. Its orbital eccentricity measures 0.999366929, a value exceedingly close to 1, indicating a path that is almost open. An eccentricity precisely equal to 1 defines a parabola, an open curve where an object originates from an infinite distance and returns to infinity. An eccentricity slightly less than 1 signifies an extremely elongated ellipse, a trajectory that requires tens of thousands of years to complete. The semi-major axis of R2's orbit is estimated to be approximately 798 astronomical units. This implies that its aphelion, the farthest point in its orbit, lies far beyond the Kuiper belt, deep within the Oort cloud. The estimated orbital period is 22,554 years. This comet last graced the inner solar system during the late Paleolithic era, a period when early humans were creating cave paintings and hunting mammoths. The inclination of its orbit is approximately 4.4747 degrees. This represents the angle between the comet's orbital plane and the ecliptic, which is the plane of Earth's orbit. A 4.47-degree inclination is considered low. Many comets originating from the Oort cloud arrive at steep inclinations, descending from random angles. R2's orbit, however, is nearly coplanar with the planets. This characteristic simplifies the prediction of its trajectory, but also means it spends more time traversing the ecliptic plane, the very region where Earth orbits. This proximity inherently increases the probability of close encounters. Its perihelion, the point of closest approach to the Sun, occurred on September 12, 2025, at a distance of 0.50347 astronomical units. This is approximately 75 million kilometers, situated just inside the orbit of Venus. At this proximity, solar heating is exceptionally intense. Surface temperatures can ascend to several hundred degrees Celsius, causing water ice to sublimate rapidly and volatiles to outgas vigorously. This is the period when comets achieve peak brightness, becoming spectacular celestial events, but also when they become inherently unstable. Now, let us consider its outward journey. R2 is currently receding from the Sun, but its trajectory intersects Earth's orbital path. On October 20th, 2025, the comet will reach its closest approach to Earth. The predicted distance will be 0.26065 astronomical units, which translates to approximately 38,925,117 kilometers. This distance is roughly 100 times the distance to the Moon. While in human terms this sounds considerable, in cosmic terms, it represents a remarkably close encounter. However, the most critical figure is the MOD, the minimum orbit intersection distance. This metric represents the smallest possible spatial gap between Earth's orbit and the comet's orbit, calculated purely geometrically, independent of their relative positions in time. For R2, the MOD is approximately 0.048 astronomical units, roughly 7 million kilometers. This means that if one were to superimpose both orbital paths in space and measure the shortest distance between them, the result would be 7 million kilometers. This is the calculated gap. If the comet and Earth were positioned unfavorably in their orbits at the same time, this gap could theoretically shrink to zero. However, this is not the case. The current orbital solution indicates that on October 20th, Earth and R2 will be separated by 39 million kilometers. The comet will pass, and we will remain safe. The models assert this. The calculations corroborate it. NASA is not issuing any public warnings. There is no impact alert, so why are we still discussing this matter? The reason lies in the inherent limitations of orbital solutions. They are derived from observational data, and all observations are subject to uncertainties. The more observations available, the more precise the understanding becomes, yet R2 was identified late in its trajectory. Consequently, our data is less extensive than ideal. While the orbital path is reasonably well defined, it lacks perfect precision. Minor deviations, such as non-gravitational forces from outgassing, shifts in the comet's rotational state, or alterations in its mass distribution, can subtly alter its course. A deviation of a few thousand kilometers might be insignificant for the main cometary body, but it becomes a considerable factor if the comet has dispersed fragments. These fragments can drift apart. If R2 has fractured, if it has separated into multiple pieces, those pieces will possess marginally different velocities. Over time, they will disperse along the comet's orbital path, forming a stream of debris. Larger fragments will exhibit less divergence. Smaller fragments, dust particles and pebbles, however, can spread out extensively. If Earth traverses this debris stream, an increase in meteor activity will be observed, potentially escalating into a meteor storm or an even more significant event. The comet's current observable brightness is estimated at magnitude 6.7 as of October 10, 2025. This is fainter than initially anticipated, but not entirely unexpected, as comets naturally dim as they recede from the Sun. The crucial question remains whether R2 will experience another outburst. Such an event, a sudden brightening, would signify renewed activity, possibly indicating further fragmentation or a fresh release of volatile materials, thereby altering the associated risks. Visualizing the situation aids comprehension. Envision the Sun at the center of our solar system. Earth's orbital path forms a nearly circular trajectory around it, spanning an approximate distance of 150 million kilometers in radius. R2's orbit, conversely, is a highly elliptical path originating from the outer solar system, sweeping close to the Sun before heading back into the void. These two orbital paths intersect, but crucially, they do not coincide in time. The comet passes through their shared intersection point in October. Earth, however, traverses the same point several months later. This creates a temporal and spatial separation. As long as this separation persists, Earth remains safe. However, comets are inherently unpredictable celestial bodies. They do not adhere to rigid schedules. They exhibit irregular movements, can fracture, and shed fragments, which then deviate from the parent object's path. These fragments drift, disperse, and can sometimes arrive at unforeseen moments. In the subsequent segment, we will explore the realm of astronomical observation, the public's fascination with celestial events, the diversions they create, and the influence of media coverage on public attention. This leads us to Part 5, the immediate celestial theater, visual observation, media convergence, and public distraction. October is shaping up to be a busy period in the night sky. Comet R2 is nearing its closest approach to Earth, with its peak proximity anticipated around October 20th. Yet, it is not the sole celestial attraction. Another comet, designated C2025A6, also known as Lemon, is likewise intensifying in brightness and becoming visible in the northern hemisphere around the same time frame. Two comets, both observable by amateur astronomers, both making their closest passes within days of each other. This confluence presents a rare and spectacular event, the kind that inspires widespread public interest and encourages skyward gazes. Adding to this celestial display is the Orionid meteor shower. The Orionids typically reach their peak activity annually between October 20th and 21st, coinciding with Earth's passage through the debris trail left by Comet Halley. Yes, Halley, the renowned comet that graces our skies approximately every 76 years. Even when Halley is distant, its residual trail of dust and ice fragments spread along its orbital path persists. Each October, Earth intersects this stream, and these particles impact our atmosphere at speeds of 70 kilometers per second. They disintegrate, igniting the atmosphere and producing streaks of light, which we perceive as meteors. The Orionids generally yield between 10 and 20 meteors per hour at their zenith, though this number can sometimes be higher. While not a major celestial storm, it is a dependable annual occurrence. Therefore, on the night of October 20th, 2025, observers will have the opportunity to witness two comets in the sky simultaneously, alongside a meteor shower at its peak intensity. The heavens will be exceptionally active. Correspondingly, media coverage will likely be extensive. Astronomy enthusiasts will inundate social media platforms with photographic captures. News organizations will feature narratives detailing this astronomical spectacle. This confluence of events creates an ideal scenario for public engagement with astronomy. It also presents a perfect opportunity for distraction, because while the public is captivated by the Orionids, while astrophotographers are diligently capturing images of the two comets, and while headlines trumpet the splendor and wonder of the cosmos, a considerably smaller number of individuals will be posing the more pressing inquiries. How precise is our knowledge of R2's trajectory? What is the margin of error in its orbital determination? Has it undergone fragmentation? Are we actively monitoring its debris? What are the potential ramifications should an unforeseen event occur? The Washington Post reported on the dual comet event, highlighting that both R2 and Lemon would be visible to individuals equipped with binoculars or small telescopes. Their reporting emphasized the rarity and beauty of the occasion, focusing on the chance to observe two comets concurrently. However, they did not prominently feature the comet's proximity to Earth. The concept of minimum orbit intersection distance, MOID, was not mentioned, nor was the potential risk associated with fragmentation discussed. This is not a critique of their coverage, but rather an observation on the nature of public science communication. Spectacle garners attention. Risk assessment, less so. Furthermore, the Interstellar Object 3 Atlas continues to dominate headlines, despite its predicted closest approach being 1.8 astronomical units, a distance considered safe by any standard. The media finds 3 Atlas compelling due to its enigmatic nature, its origin from another star system, its variable coloration, sometimes appearing red, at other times green, depending on the observational data, and its apparent color shifts are intriguing. Such behavior is unusual for asteroids. This has fueled speculation regarding artificial origins, the possibility of alien probes, and encoded messages within its trajectory. While highly improbable, these narratives are undeniably captivating, shareable, and conducive to generating online engagement. In contrast, R2, the closer celestial visitor with an uncertain orbit and a history of outbursts, receives considerably less prominent media attention. It is perceived as less exotic, being a native of our solar system, likely originating from the Oort cloud. There is nothing interstellar about it. It is simply another comet. Except, it is not. It is a comet that evaded detection until it was remarkably close. It is a comet that remained hidden in the sun's glare, emerging only after completing its perihelion pass. It is a comet that may have already fragmented and could potentially do so again. It is a comet whose minimum orbit intersection distance, MOID, is 7 million kilometers, a distance considered uncomfortably small. Public perception is significantly influenced by novelty. 3 Atlas embodies this novelty. R2, by comparison, does not. Consequently, 3 Atlas captures the headlines, while R2 is relegated to a mere footnote. However, footnotes can harbor hidden dangers. They can obscure crucial information. It is imperative to acknowledge certain behavioral considerations here. Comets are not reliable performers in terms of predictability. Their brightening and dimming occur without warning. Fragmentation can happen unexpectedly. Predictions are essentially informed hypotheses based on past behavior, but each comet is unique. R2 might brighten to magnitude 4, becoming visible to the naked eye. It might fade to magnitude 8, disappearing from view. It could fragment into multiple pieces, creating a debris field. Or it might exhibit no significant activity and quietly recede into the outer solar system, largely forgotten within a year. These possibilities remain unknown. What is certain is that this scenario does not constitute an impact alert. The current orbital calculations indicate that R2 will pass Earth at a distance of 39 million kilometers. This distance is insufficient for a direct collision, but it is close enough to present other potential hazards. It is close enough for interactions with debris, close enough to cause increases in meteor flux, and close enough that if the comet fragments unexpectedly, some of its pieces could be propelled onto Earth-crossing trajectories. This is the fundamental nature of cosmic risk. It is not a binary state of safe or doomed. Instead, it is probabilistic, characterized by uncertainty and layered with numerous contingencies. Our current detection systems, the network of telescopes and surveys we rely upon for early warnings, are not engineered to manage such contingencies. They are designed to track predictable objects on stable orbits. When unpredictable events occur, when an object conceals itself in glare, brightens suddenly, or sheds fragments, both the system and we, as its operators, face significant challenges. Next, we will delve deeper into past near misses, examining asteroids that passed Earth with minimal warning and highlighting detection failures that occur more frequently than publicly acknowledged. This brings us to Part 6, case studies of asteroids discovered just prior to or after their close encounters. In early 2025, an asteroid designated 2025 TF made a pass within approximately 400 kilometers of Earth's surface. 400 kilometers is closer than the International Space Station orbits. It is closer than most satellites. It is within the operational altitudes of numerous space assets. And remarkably, we did not detect it until it was almost upon us. 2025 TF is presumed to be small, likely only a few meters in diameter. At that size, even if it had entered the atmosphere, it would have disintegrated, producing a brilliant fireball but causing no ground-level damage. In comparison, the Chelyabinsk meteor in 2013, estimated to be between 17 and 20 meters in diameter, exploded in the atmosphere with a force equivalent to several hundred kilotons of TNT. While it shattered windows and injured over 1,500 people, it did not create a crater. 2025 TF, being smaller, would have presented a visual spectacle, nothing more. However, the critical point is not its size, but the detection latency. We failed to detect it until it was virtually overhead. Its trajectory carried it over Antarctica, one of the Earth's most remote regions, where very few observers were present. Had it arrived a few hours earlier or later, or had its trajectory been slightly different, it might have passed over a populated area, and we would have had no prior warning. This is not an isolated incident. In recent years, several small asteroids have been identified only days, hours, or even minutes before their closest approach to Earth. Some were detected only after they had already passed us. They traversed Earth's vicinity, invisible to our survey systems, and we only became aware of them on their outward journey. This phenomenon occurs because our detection network has inherent limitations. Telescopes have minimum sensitivity thresholds, and small objects are inherently faint. If they approach from the direction of the sun, they are obscured. If they move at high velocities, they traverse the sky too rapidly for automated survey systems to acquire them. Dark objects, those with low albedo, reflect minimal sunlight and effectively blend into the background. This detection bias is not merely a theoretical concern. It represents a practical and observable failure mode. We miss objects. This occurs frequently, and we typically only realize our oversight when an observer happens to be looking at the correct patch of sky at the opportune moment and notices an anomaly in motion. The consequences of such missed detections can be more severe than one might initially assume. While it is true that most small asteroids burn up harmlessly in the atmosphere, this is not universally the case. Even a relatively small object, if it impacts a critical target, can inflict catastrophic damage. A few meters of rocky material striking a satellite at orbital velocity would result in its instantaneous destruction. A collision with the International Space Station would have dire, potentially fatal, consequences. An impact on a densely populated city, even from a modest-sized impactor, could level buildings and cause thousands of fatalities. The Earth's atmosphere serves as a protective shield, but it is not an infallible one. Objects exceeding approximately 20 meters in diameter can survive atmospheric entry and reach the surface. Even smaller objects can still generate destructive airbursts. Furthermore, there is the issue of fragmentation debris. When an asteroid breaks apart within the atmosphere, it disperses fragments over a wide geographical area. While most fragments are small, some can be substantial enough to cause damage. If this atmospheric breakup occurs over a densely populated region, those fragments transform into deadly projectiles. The Chelyabinsk event, for instance, scattered meteorites across hundreds of square kilometers, with some individuals collecting them as souvenirs. However, had the impacting object been larger, or had the fragmentation occurred at a lower altitude, the resulting fragments would have posed a significantly greater hazard. Now, let us scale this scenario up. Instead of a single small asteroid, imagine a cloud of debris originating from a fragmenting comet. Instead of a few meters of rock, envision hundreds or thousands of pieces, ranging in size from dust grains to sizable boulders, dispersed along the comet's orbital path. Instead of a singular point of impact, Conceive of a diffuse threat, a statistical hazard where the probability of any individual piece striking a specific target is low. However, the aggregate probability, the cumulative chance of an impact occurring somewhere, becomes non-negligible. This is the consequence of cometary fragmentation. They do not produce a single projectile, but rather a widespread dispersal of potential hazards, akin to a shotgun blast. R2 possesses a minimum orbit intersection distance, MOID, of 7 million kilometers. This represents the closest proximity between Earth's orbital path and the comet's own orbit. If the comet were to fragment, and if its constituent pieces were to spread along its orbit, some of these fragments could drift closer to Earth's trajectory, not necessarily to the point of zero separation, and certainly not to impact, but closer. Close enough that the statistical probability shifts from negligible to a small but non-zero value. And for risk analysts, a small but non-zero probability is a cause for significant concern. This underscores the critical lesson learned from 2025 TF and similar events. Detection latency is a tangible reality. We do not detect everything. We miss most objects if they are small, fast-moving, or approaching from unfavorable directions. The asteroids we successfully track are those that adhere to predictable patterns. They arrive on well-defined trajectories from known directions at expected times. Those that deviate from these norms, the unpredictable ones, are the objects that instill apprehension because they are the ones that evade our detection capabilities. Next, we will investigate how comets can pose a threat even without direct impact, examining how their debris trails and dispersed dust can create persistent hazards long after the parent object has moved on. This leads us to Part 7, Comet Fragmentation and the Hazard of Dust Trails, presenting realistic speculative scenarios. Even if a comet misses Earth, its debris can still inflict harm. Let me elaborate on this mechanism. Comets are not solid, monolithic bodies. They are loosely aggregated structures composed of ice, dust, rock, and organic compounds, held together by weak gravitational forces and surface tension. This makes them inherently fragile. As they approach the sun, thermal stresses induce fracturing. Outgassing generates internal pressure that can cause them to split apart. Tidal forces, if a comet passes too close to a massive celestial body, can tear it asunder. Sometimes, fragmentation occurs subtly, shedding small pieces. At other times, it is a spectacular disintegration, breaking into numerous fragments. The comet Shoemaker-Levy 9 serves as a well-known illustration of this phenomenon. In 1992, it ventured too close to Jupiter and was torn apart by the planet's powerful tidal forces. The resulting fragments, numbering over 20, dispersed along its orbital path. 2 years later, they systematically collided with Jupiter, triggering colossal explosions that were observable even from Earth. Each impact unleashed energy comparable to millions of nuclear bombs. The atmospheric disturbances on Jupiter persisted for months. While awe-inspiring, this event starkly demonstrated the fragility of comets and the potential danger posed by their fragments. Another pertinent example is Comet 73P Schwarzmann-Wachmann. This comet has undergone multiple fragmentation events. In 1995, it fractured into several pieces. In 2006, it fragmented again, this time yielding dozens of smaller chunks. Observers witnessed its disintegration in real time, with each fragment developing its own coma and tail. These fragments continued to spread, each following a slightly divergent trajectory. Over time, they coalesced into a debris stream, a celestial river of ice and dust flowing along the comet's original orbital path. Earth has periodically passed through portions of this stream, resulting in a temporary surge in meteor activity. While not catastrophic, these events were noticeable. Now, let us apply this understanding to R2. The comet has already exhibited at least one outburst, which strongly suggests inherent instability. If it undergoes fragmentation, its constituent pieces will diverge. The rate of divergence is contingent upon their relative velocities, which in turn depend on the energy released during the fragmentation event. A gentle separation leads to slow dispersal, whereas a violent explosion results in rapid spreading. Regardless of the mechanism, over time, the fragments will disperse, and so will the dust they continuously shed. Dust represents a significant hazard. All comets continuously release dust as their ices sublimate. These dust particles are minute, ranging from microns to millimeters in size, yet they travel at speeds of tens of kilometers per second. At such velocities, even a grain of sand possesses immense kinetic energy. If a dust particle impacts a spacecraft, it can puncture its hull. If it strikes a satellite, it can damage solar panels, sensors, or communication equipment. If it hits an astronaut during a spacewalk, the consequences could be fatal. The International Space Station, for example, is equipped with shielding designed to protect against micrometeoroids. This shielding consists of multiple layers, engineered to vaporize incoming particles before they penetrate the hull. However, these shields are not infallible. Larger particles or those arriving at unusual angles can breach the defenses. The ISS has sustained multiple impacts. While most strikes cause minor damage, some have necessitated repairs. A dense meteoroid stream, such as one produced by a fragmenting comet, substantially elevates the risk. Now, consider the geometrical aspects. R2's minimum orbit intersection distance, MOID, is 7 million kilometers. This is the closest approach between the comet's orbital path and Earth's orbit. If the comet fragments and its fragments spread along its orbit, some of these pieces might drift closer to Earth's path. Not necessarily to zero distance, and not to impact, but closer. And if Earth traverses this debris stream at an inopportune moment, we could encounter a significantly higher flux of particles. This could manifest as an enhanced meteor shower, potential damage to satellites, or an increased incidence of micrometeoroid impacts on spacecraft. The probability of any single particle striking a specific target is low. Space is vast, and targets are relatively small. However, the aggregate probability, the chance that something, somewhere, will be impacted, is higher. And the number of objects in orbit today is substantial, comprising thousands of satellites, space stations, and various spacecraft, all of which are potential targets. Furthermore, there is the scenario of atmospheric interaction. If Earth passes through a dense dust stream, even if the particles are small, the cumulative effect could be observable. High-altitude airglow might increase. Bolide activity, bright meteors that explode in the upper atmosphere, might spike. Amateur astronomers would notice these anomalies, and meteor observation cameras would record unusual patterns. While not catastrophic, such events would be atypical and could trigger alarms. The genuine concern lies not with the dust we can readily observe, but with the fragments we cannot. A boulder-sized chunk, approximately 1 to 2 meters in diameter, traveling at 30 kilometers per second, would be virtually invisible until it was too late for any meaningful action. Optical surveys might detect it, but only if they were coincidentally directed at the correct patch of sky at the precise moment. If the fragment approached from the direction of the sun, it would remain unseen. If it possessed a dark, low albedo surface, detection would be exceedingly difficult. And if it entered the atmosphere over a populated area, the result could be an event comparable to Chelyabinsk, or potentially worse. Estimating the probability in such cases is challenging. We do not possess definitive knowledge regarding whether R2 has fragmented, if it will fragment, the number of pieces it might produce, or how they might disperse. We are also unaware of the distribution of fragment sizes, velocities, or trajectories. All we have is the orbital path of the parent comet and a 7 million kilometer gap between that orbit and Earth's trajectory. Within these parameters, we can assert that the probability of a fragment impacting Earth is low. However, low is not synonymous with zero, and when the consequences of miscalculation are measured in human lives and critical infrastructure, a low probability may not be sufficiently reassuring. Visualization again proves helpful. Imagine the comet's orbit as a fine thread suspended in space. Now, envision that thread fraying and splitting into dozens or even hundreds of smaller, distinct threads, each following a slightly altered path. Some of these threads will remain close to the original course, while others will deviate. This collection of threads will spread over time, forming a diffuse ribbon extending along the orbit. Earth's orbit, another thread, intersects this ribbon at an angle. Most of the time, Earth passes through unoccupied space. However, on occasion, it crosses the ribbon, and as it does, the particles within the ribbon rain down. This scenario is not without precedent. Meteor showers are precise manifestations of this phenomenon. The Perseids, the Leonids, and the Orionids are all debris streams originating from comets. Annually, Earth traverses these streams, resulting in visible meteor activity. While generally harmless, these events can occasionally be spectacular and very rarely dangerous. In 1833, the Leonid meteor storm produced tens of thousands of meteors per hour. Witnesses described the sky as ablaze. If such an event were to occur today, given our extensive satellite infrastructure, the resulting damage would be severe. R2 is not predicted to generate a meteor storm. Its debris, if it exists, is likely too sparse. However, this remains an unknown. We cannot ascertain the precise nature of the threat until it is directly observed. And by the time we observe it, it may be too late to take any action other than to witness the unfolding events. Moving forward, we will pose a more profound question. Are we witnessing an actual surge in unexpected celestial visitors, or is this merely a consequence of observational bias? Is the solar system indeed dispatching more objects towards us, or are we simply becoming more adept at detecting them? This leads us to Part 8, Pattern Recognition. Are we observing an increase in surprise visitors? Allow me to enumerate them. Oumuamua arrived in October 2017, marking the first confirmed interstellar object detected passing through our solar system. Its characteristics were peculiar, elongated, exhibiting erratic tumbling, and accelerating in ways that could not be explained by standard outgassing models. It vanished before we could properly examine it. Then, in August 2019, Borisov arrived, our second visitor from beyond the solar system. This one was undeniably a comet, complete with a luminous envelope, a trailing tail, and a chemical makeup that strongly suggested it originated from the remnants of another star. Now, we have 3 Atlas, a discovery made in 2025. This is yet another object from outside our solar system, though whether it's an asteroid or a comet's nucleus depends on who you ask. Its color fluctuates, which is quite peculiar. And while the world is focused on 3 Atlas, R2 made its stealthy entrance from our own cosmic neighborhood, remaining undetected until after it passed its closest point to the Sun. That's 4 such objects in just 8 years: Oumuamua, Borisov, 3 Atlas, and R2, each with distinct origins, varied compositions, and unique discovery circumstances, yet all of them were entirely unexpected. Each arrived with minimal or no prior warning. Is this a trend? Is this a surge in activity? Or is it simply the result of us finally paying closer attention? Three main hypotheses exist to explain this phenomenon. The first posits an observational bias. Our instruments have become significantly more sophisticated. We have more telescopes, broader sky surveys, and an increasing number of amateur astronomers with access to data comparable to professional-grade information. Simply put, we are searching more diligently, and consequently, we are discovering more. Survey systems like Pan-STARRS and the forthcoming Vera C. Rubin Observatory are specifically engineered to detect fleeting events, moving celestial bodies, and anything that undergoes change. As these systems become operational and their capabilities advance, our detection rate naturally increases. This doesn't necessarily imply an actual rise in the number of objects arriving, but rather that we are finally discerning the celestial bodies that have always been present. The second hypothesis suggests a genuine increase in dynamical flux. It's possible that something is disturbing the Oort cloud, perhaps a star that passed by long ago, sending a ripple of comets inward, and we are only now witnessing the initial arrivals. Alternatively, our solar system might be traversing a region of space with a higher concentration of interstellar debris. Gravitational influences from the Milky Way's structure, known as galactic tides, could be nudging more comets towards the inner solar system. This scenario is not implausible. The Oort cloud is an immense reservoir, estimated to contain trillions of comets. Even a minor gravitational disturbance could propel thousands of these icy bodies inwards over the span of a few thousand years. From our human perspective, constrained by our relatively short lifespans, this could appear as a sudden influx. The third hypothesis is statistical clustering. This suggests that the observed frequency is merely a matter of pure coincidence. Random processes inherently produce clusters. If you flip a coin 100 times, you are likely to observe runs of heads or tails. This does not indicate that the coin is biased. It merely demonstrates the clumping nature of randomness. 4 unexpected visitors in 8 years could simply be statistical noise, a random fluctuation without any deeper underlying significance. It is entirely possible that in the subsequent 8 years, we might detect none, or conversely, as many as 10 such objects. Without additional data, differentiating between a genuine signal and random noise remains challenging. Each of these hypotheses is supported by evidence. The argument for observational bias is particularly strong. The number of known near-Earth asteroids has surged dramatically over the past 2 decades, not due to an increase in their sudden appearance, but rather because we initiated systematic searches for them. The same logic likely applies to comets. The Solar and Heliospheric Observatory, SOHO, has discovered thousands of comets, many of them sun grazers, simply because its vantage point allows it to observe phenomena invisible to optical telescopes. As our detection network expands, so does our catalog of observed objects. However, observational bias alone doesn't account for every anomaly. Oumuamua, for instance, was genuinely perplexing. Its elongated shape, its non-gravitational acceleration, and its lack of a discernible coma defied straightforward explanations. Some astronomers proposed it was a fragment of a planet shattered by tidal forces within another star system. Others suggested it was an iceberg of hydrogen or nitrogen, a shard of frozen gas. These increasingly exotic hypotheses arose because simpler explanations failed to fit the observed data. Ultimately, it departed, and we lost the opportunity for further study. 3 Atlas also presents a puzzle. Its color appeared to shift from red to green, depending on the observations one trusts. Asteroids do not typically exhibit such color changes. Color is intrinsically linked to surface composition, and a change in color suggests a variation in composition, implying the surface is not uniform. It might be rotating, revealing different sides that reflect distinct wavelengths of light. Perhaps it is subtly outgassing, with its coma altering the observed spectrum. Or it could be something entirely different altogether. The truth remains elusive because we have not been able to get close enough to resolve its details. R2 fits the pattern in a different manner. It is not an interstellar object. It is native to our solar system, likely originating from the Oort cloud. However, it remained hidden within the sun's glare, emerging only after its perihelion passage, demonstrating how easily we can overlook objects, even within our own immediate surroundings. If R2 could evade detection, so can others. How many long-period comets traverse the inner solar system annually without being detected? We simply do not know. We only observe those that become sufficiently bright, remain visible for an adequate duration, or cross our detection thresholds. The rest remain unseen specters. So, is there a pattern? Perhaps. The optimistic interpretation is that we are becoming more adept at perceiving the universe as it truly is, teeming with transient visitors, streams of debris, and unexpected arrivals. The pessimistic outlook suggests that the rate of these arrivals is escalating, and we are unprepared. The most realistic perspective likely lies somewhere in between. We are observing more because our search efforts are more intensive. However, we are also discovering that the baseline rate of cosmic traffic is considerably higher than we previously assumed. Our solar system is not a tranquil region. It is a bustling highway, and we are only now beginning to install traffic monitoring systems. Our next focus will be on the institutions responsible for managing this celestial traffic, examining their data processing pipelines, identifying bottlenecks, and investigating the silences that foster suspicion. This segment, titled Institutions, Silence, and the Information Lifecycle, will guide you through the process by which a discovery transforms into public knowledge. An observer, whether a professional astronomer or an amateur enthusiast, identifies something unusual, a moving object, a source that has increased in brightness, or a transient event. They meticulously record its position, the exact time of observation, and its apparent magnitude. Their next step is to verify if this object has already been documented. If it is a new discovery, they submit a report. The designated reporting body is the Minor Planet Center, MPC, which is managed by the International Astronomical Union. The MPC serves as the central clearinghouse for observational data pertaining to asteroids, comets, and other small celestial bodies. It aggregates observations from a global network of observers, rigorously verifies this data, and issues official circulars upon confirmation of a new celestial object. However, the verification process requires time. A single observation is insufficient for confirmation. Multiple observations are essential to ascertain the object's reality, rule out instrumental artifacts, and calculate a preliminary orbital path. This necessitates waiting for other observers to direct their telescopes towards the same patch of sky and confirm the sighting. If the object is faint, near the detection limit, or moving rapidly, the confirmation process can extend over several days, or sometimes even longer. Once confirmed, the MPC assigns a provisional designation and disseminates an electronic circular. The data is publicly accessible to anyone interested, but it comprises raw observational parameters, orbital elements, position vectors, and magnitude estimations. This is not a press release. It is not a headline designed for mass consumption. Rather, it is a highly technical document intended for astronomers. The general public does not typically consult MPC circulars. Instead, they rely on news articles, which, if published at all, appear at a later stage. Meanwhile, other institutions refine the orbital calculations. The Jet Propulsion Laboratory, JPL, operates the Horizon System, a sophisticated tool for calculating precise trajectories of solar system objects. As more observations become available, the accuracy of the orbital solutions improves, uncertainties diminish, and predictions become more reliable. If an object is deemed potentially hazardous, meaning its orbit brings it into close proximity with Earth, JPL flags it accordingly. The Center for Near-Earth Object Studies, CNEOS, then evaluates the associated risk. If the risk level is sufficiently high, NASA will issue a public statement. If the risk is deemed low, such a statement may not be released. For R2, the process unfolded as follows. Vladimir Bazugi, an amateur astronomer, detected the object in SOHO data on September 11, 2025. He promptly reported his findings. Subsequent observations by other astronomers optically confirmed the object's existence. The MPC issued a circular assigning it the designation C2025R2. JPL subsequently calculated its orbit, and CNEOS evaluated the potential threat. The conclusion was that R2 posed no danger, with its closest approach projected to be 0.26 astronomical units, a distance deemed sufficiently safe. Consequently, no press release was issued, and no public warning was disseminated. It remained a technical update embedded within a database. This is where the silence begins. It is not born from any deliberate attempt to conceal information or from a conspiracy, but rather from the system's design, which prioritizes risk mitigation over public engagement. If an object is not considered a threat, it does not generate headlines. And if it doesn't make headlines, the majority of the public remains unaware of its existence. R2 received mention in a few astronomy-focused publications and a handful of space news websites. It was even featured as the astronomy picture of the day on September 18th. However, it did not trend on social media, nor did it dominate the news cycle. It was perceived as just another comet, one of dozens discovered annually. Contrast this with 3 Atlas, an interstellar object exhibiting mysterious color changes and peculiar acceleration. These are the elements that create headlines. This is the kind of narrative that captivates mainstream media, gains traction on social platforms, and sparks discussions in online forums. The fact that 3 Atlas poses no threat, that its closest approach is 1.8 astronomical units, and that it presents no danger, is secondary to its inherent intrigue, and intrigue is a commodity that sells. This situation creates a void when official institutions fail to provide timely and accessible updates. When the flow of information is slow and technical, and the interval between discovery and public awareness stretches to weeks or even months, speculation inevitably fills the vacuum. Social media users observe these discrepancies and voice their questions. Why aren't we hearing more about this? Why is the coverage so limited? Is something being kept from us? In the absence of official explanations, unofficial narratives emerge, giving rise to theories, conspiracies, and rumors. Vladimir Bazugi's discovery of R2 serves as a pertinent illustration. He is not a professional astronomer, nor does he hold a position within a space agency. He is an amateur with the expertise to analyze SOHO data. The fact that he identified the comet before the professional surveys did is not indicative of a failure on their part, but rather a reminder that our detection network is not impenetrable, that unconventional pathways to discovery are valuable, and that sometimes the most crucial observations originate from unexpected sources. However, this also raises further questions. If an amateur can discover a comet that eluded professional surveys, what else might we be missing? How many objects traverse the inner solar system undetected because they happen to be in the wrong place at the wrong time, or because the surveys are focused elsewhere, or due to factors like excessive sky brightness, adverse weather conditions, or instrument downtime for maintenance? We do not know. We cannot know. This is the fundamental problem. The information life cycle is deliberately paced. Verification procedures are in place to prevent false positives, and caution is exercised to avert public panic. However, this caution also creates information gaps, which in turn breed doubt. When individuals lose faith in institutions to provide accurate information, they seek alternative sources, and these alternative sources are not always reliable. In our next segment, we will critically examine wild card ideas, conspiracy theories, and fringe claims, distinguishing between those that warrant serious consideration and those that do not. This will be presented in Part 10, Wild Cards and Conspiracies. Let me be explicit. Some individuals will assert that R2 is not a natural celestial body. They will contend that it is a probe, a craft, or an engineered device dispatched by an extraterrestrial entity for observational purposes. They will argue that its trajectory is suspiciously convenient, its timing too perfect, and its outburst too deliberately controlled. They will claim that NASA possesses undisclosed knowledge, that images are being withheld, and that the true data is classified. They will propose that this represents a message, a warning, or a test, and they will firmly believe these assertions. Therefore, let us undertake a careful assessment. We will examine these claims individually to determine which ones merit any degree of attention. Claim 1. R2 is an artificial object. Is this physically plausible? In principle, yes. Any civilization sufficiently advanced could construct a spacecraft designed to resemble a comet. They could coat it with ice to generate a coma when subjected to heat. They could program it to produce outbursts at specific intervals. They could engineer its trajectory for a close approach to Earth. While theoretically possible, it is not a simple undertaking and would inevitably leave detectable traces. If R2 were artificial, we would anticipate observing anomalies. Spectroscopic analysis would reveal unusual elemental or molecular compositions that deviate from natural cometary chemistry. The nucleus would likely exhibit structural regularities or geometric patterns not found in natural objects. Its trajectory would show precise control, with minor adjustments inconsistent with natural outgassing phenomena. Furthermore, there would likely be detectable electromagnetic emissions, such as radio signals or infrared signatures, indicating the presence of active systems. We have not observed any such evidence. The spectrum appears consistent with that of a normal comet. The coma is readily explained by sublimating ice. The trajectory aligns with gravitational dynamics. There are no detectable signals. Occam's razor dictates that the simplest explanation is typically the most accurate. R2 exhibits characteristics of a comet because it is, in fact, a comet. Invoking an artificial origin necessitates the introduction of additional assumptions, increased complexity, and the postulation of unknown actors with indeterminate motives and capabilities. While possible, it is not a necessary explanation. In scientific inquiry, we refrain from proposing explanations that are not fundamentally required. Claim 2. The images are being suppressed. Are we seeing the entirety of the available visual data? Almost certainly not. Professional observatories do not publish every image they acquire. They engage in data processing, calibration, noise filtering, and the selection of optimal frames. Some data is proprietary, reserved for the research teams that initiated the observations. Other data may be of insufficient quality to warrant public release. However, suppression implies intent, a deliberate, coordinated effort to withhold information. Such an undertaking would require a level of coordination that is exceptionally difficult to achieve. Observatories are geographically dispersed and operate autonomously. Amateur astronomers possess their own equipment. If a visually dramatic event were occurring, it is highly probable that someone would share it online. The absence of compelling visual evidence suggests that no such dramatic images exist, rather than implying that they are being deliberately concealed. Claim 3. The trajectory is manipulated. Could an external force be steering R2? If by external force you are referring to extraterrestrial intelligence, then we are back to the first claim. If, however, you are referring to natural forces, then the answer is yes. Outgassing is responsible for non-gravitational accelerations. Comets are not purely ballistic objects. They alter their trajectories by venting gas. R2 has exhibited outbursts, indicating that it is releasing gas, which in turn influences its path. JPL's orbital models incorporate these non-gravitational forces, accounting for outgassing. While trajectory predictions are not perfectly precise, they are generally accurate. If the comet were under active control, we would expect to observe deviations from these models that could not be attributed to outgassing. We have not detected such deviations. Claim 4. This is harmless but symbolic. Some individuals argue that even if R2 poses no threat and is not destined to impact Earth, its arrival carries significance, acting as a sign, an omen, or a synchronicity. This is not a scientific assertion. It is a philosophical or spiritual claim. Science can accurately determine an object's orbit, its composition, and the probability of an impact. However, it cannot ascertain whether the universe is conveying a message, as this falls outside the purview of empirical investigation. If you find personal meaning in the arrival of a comet, that is your prerogative. However, it is crucial not to conflate personal interpretations with physical risks. Now, are there any claims that warrant closer examination? Yes. 1. The possibility of fragmentation and the associated debris hazards is a genuine concern. This is not a conspiracy theory. It is a matter of physics. If R2 were to fragment or shed pieces that diverge from its primary trajectory, those fragments could pose a hazard. While not necessarily an impact hazard, they could create a debris field, increasing the micrometeoroid flux and potentially threatening satellites. This is a scenario worth monitoring and preparing for. It remains speculative, but is grounded in our understanding of cometary behavior. The triage matrix can be summarized as follows. Artificial origin is not feasible without supporting evidence. Image suppression is unlikely given the distributed nature of astronomical observation. Trajectory manipulation is not supported by evidence beyond natural outgassing. Symbolic meaning lies outside the scope of scientific inquiry. Fragmentation and debris are plausible and merit ongoing tracking. Speculation is an enjoyable aspect of human nature. It is our tendency to perceive patterns, imagine agency, and fill informational voids with narratives. However, we must always be prepared to rigorously test these narratives against empirical data. And when the data contradicts the narrative, we must possess the discipline to abandon the story and move forward. Moving on, we will now shift our focus to other recent scientific headlines, beginning with neuroscience, as the brain itself functions as a detection system, complete with its own blind spots. This will be presented in Part 11, Neuroscience. UCSF identifies a protein that slows brain aging. In August 2025, researchers at the University of California, San Francisco, published findings regarding a protein that appears to regulate the aging process of the brain. In experiments conducted on aged mice, this protein seemed to act as a brake on neural plasticity. When the researchers inhibited the activity of this protein, the aged mice demonstrated improvements in memory and learning capabilities. Their neurons exhibited more reliable firing patterns, and their synaptic connections became stronger. By several measures, their brains began to function in a manner analogous to younger brains. The experimental protocol was straightforward. Take old mice, identify the protein that accumulates with age, block its function using either a drug or genetic manipulation, and then assess whether behavioral improvements were observed. The results were encouraging. Aged mice that underwent this treatment performed better on memory-related tasks, navigated mazes more swiftly, and recognized objects with greater reliability. The observed effects were quantifiable, reproducible, and statistically significant. However, it is important to acknowledge that these are findings from experiments with mice. Mice are not humans. Their brains are simpler, smaller, and organized differently. What proves effective in a mouse does not always translate to humans. The history of neuroscience is replete with treatments that have successfully alleviated conditions in mice, only to fail in human clinical trials. For example, Alzheimer's disease has been effectively cured in mice numerous times, yet humans continue to await a breakthrough. Therefore, caution is essential. While the findings are exciting, they remain preliminary. Nevertheless, the implications, should they prove translatable to humans, are enormous. Cognitive decline is one of the most feared aspects of aging. Memory loss, difficulties with learning, and a general slowing of cognitive processing can significantly impact independence and self-identity. If the inhibition of a single protein could decelerate or even reverse this decline, the impact would be profound, not only for individuals, but also for societies grappling with aging populations. The global economic burden of dementia is measured in trillions of dollars. A treatment that could delay its onset by even a few years would result in substantial savings of resources and alleviate immense suffering. However, complications exist. Proteins do not operate in isolation. They are integral components of complex networks, cascades, and feedback loops. Inhibiting one protein could trigger downstream effects, potentially disrupting other bodily systems. While the aged mice in the study did not exhibit apparent side effects, the observation period was relatively short. Long-term consequences remain unknown, and human physiology is considerably more complex. We live longer lives, accumulate more cumulative damage, and often have multiple coexisting health conditions. A treatment that acts cleanly in a mouse might interact unpredictably with human biology. Consider this analogy. The brain is a sophisticated detection system. It constantly scans the environment, processes incoming signals, forms memories, and generates predictions. When functioning optimally, it captures intricate details and adapts readily. As it ages, its sensitivity diminishes. Signals become weaker, noise intrudes, and discerning patterns becomes increasingly difficult. The protein identified by the UCSF researchers appears to be implicated in this degradation process. By blocking its activity, the researchers were able to restore some of the brain's youthful sensitivity. Now, let us draw a parallel to our astronomical detection systems. Telescopes scan the celestial sphere, process signals, catalog objects, and predict trajectories. When functioning optimally, they can detect faint comets, track asteroids, and provide early warnings of potential hazards. However, these systems also degrade over time. Instruments age, sensors drift, calibration accuracy decreases, data pipelines become burdened with noise, and consequently, we begin to miss objects that we were previously able to detect. While the analogy is not perfect, it is instructive. Both systems, the human brain and astronomical telescopes, are designed to identify patterns within noisy environments. Both are susceptible to degradation over time, and both can, at least partially, be restored through intervention. For the brain, this intervention might involve a protein-blocking drug. For telescopes, it might entail recalibration, sensor replacement, or the implementation of upgraded algorithms. The underlying principle remains consistent. Maintaining vigilance requires ongoing maintenance. The UCSF study serves as a crucial reminder that unseen forces dictate what registers in our perception and what evades our notice. At times, these forces are biological, such as the accumulation of a protein as we age. Other times, they are technological, like a sensor gradually drifting from its calibrated position. Occasionally, they are institutional, akin to a survey schedule riddled with omissions. The remedy, however, invariably follows the same blueprint. Identify the underlying mechanism, comprehend its operational principles, and then implement an intervention to reinstate proper functioning. Our next segment will delve into another headline from the realm of neuroscience, this time focusing on Alzheimer's disease, as dissecting the pattern of overstated claims juxtaposed with sober realities offers valuable insight. This is part 12, the Alzheimer's reversal headline. October of 2025 witnessed another surge of sensational headlines proclaiming the reversal of Alzheimer's in mice. The accompanying articles were delivered with palpable excitement, and social media posts resonated with hope. However, the actual situation was considerably more nuanced. Scientists had been evaluating a novel intervention, possibly aimed at vascular repair, or perhaps the elimination of amyloid plaques, or even the regulation of protein levels. The specifics differed depending on the particular research paper one consulted, yet the central theme remained constant. Aged mice exhibiting cognitive impairments demonstrated marked improvement following the treatment. Their brains showed a reduction in plaque buildup, their memory recall capabilities enhanced, and in certain quantitative measures, the underlying pathology appeared to reverse. This scenario is not unprecedented. Over the past 2 decades, Alzheimer's research has yielded a plethora of promising findings from studies conducted on mice. These have included vaccines designed to clear amyloid deposits, drugs intended to reduce tau tangles, and gene therapies aimed at restoring synaptic function. While these interventions have proven effective in mice, the vast majority have ultimately failed when applied to human subjects. The discrepancy between animal models and human outcomes is substantial. Mouse models of Alzheimer's do not fully recapitulate the complexity of the human disease. Mice have significantly shorter lifespans, preventing them from developing the full spectrum of pathological changes observed in humans. Their brains are structurally simpler, their immune systems differ, and their metabolic rates are accelerated. Consequently, a treatment that demonstrates efficacy in a 6-month study with mice might prove entirely ineffective in a 10-year human clinical trial. The magnitude of the study group also plays a critical role. Mouse studies frequently involve only dozens of animals, whereas human trials necessitate the participation of thousands of individuals. The The duration of the investigation is another key factor. Mouse studies typically span months, while human trials extend over years. The issue of side effects is equally paramount. A compound deemed safe for mice could exhibit toxicity in humans. Finally, efficacy itself is subject to translation. A treatment that boosts memory by 20% in mice might only achieve a 5% improvement in humans, a figure that may not be clinically significant. The Newsweek summary, much like numerous other popular science articles, placed a strong emphasis on the positive aspects: reversal, breakthrough, hope, concepts that readily capture public attention. Conversely, the original research papers, the primary sources, adopted a more measured tone, employing terms such as preliminary, limited, and requires further study. They openly acknowledged the challenges inherent in translating findings from one species to another, refraining from any claims of definitive victory, opting instead to report progress. The fundamental problem lies in the oversimplification of complex scientific endeavors into sensational headlines, where nuance is lost and uncertainty is eradicated. This widens the chasm between what researchers actually discovered and the public's perception of those findings. Consequently, when a treatment ultimately proves ineffective in humans, or a clinical trial yields negative results, the public often feels a sense of betrayal, having been led to expect a cure only to face another disappointment, eroding trust in the scientific process. This recurring pattern is not exclusive to Alzheimer's research. It manifests across all fields where high stakes and intricate science converge, including cancer research, climate science, infectious disease studies, and indeed, astronomy. When a new comet is identified, headlines often trumpet spectacular celestial displays, once-in-a-lifetime events, and visible to the naked eye sightings. The reality, however, is frequently more subdued, fraught with greater uncertainty, and heavily dependent on variables beyond our control. Comets can dim, fragment, or simply fail to meet expectations. As a result, the public, anticipating a grand spectacle, often feels let down. The appropriate response in such situations is skepticism, not cynicism. Skepticism, meaning that when you encounter a headline announcing a scientific breakthrough, it is prudent to consult the original research. Examine the sample size used in the study. Look for any qualifying statements or caveats. Inquire about what the researchers precisely measured and what conclusions they inferred. Seek to understand the limitations of the study. Ask about the projected next steps. In most instances, the answer will involve a call for more research, which is perfectly acceptable and indeed the very foundation of scientific advancement. However, this iterative process is at odds with the nature of headlines, which demand certainty. Science, on the other hand, operates within the realm of probabilities. The parallel to R2 is this: the comet itself is real, the observations made are factual, and the calculations of its orbit are accurate. However, the predictions concerning its brightness, its potential fragmentation scenarios, and its ultimate trajectory all fall within the domain of probabilities. We cannot definitively know what will transpire. Rather, we can assess what might happen with varying degrees of likelihood. The responsible approach is to communicate these probabilities clearly, without exaggeration or minimization, and certainly without resorting to sensationalism for the sake of attracting clicks. Next, we transition our focus to artificial intelligence, another domain where the gap between hype and reality is pronounced, yet simultaneously, a field where tangible advancements are revolutionizing our capacity to detect cosmic threats. This is part 13. AI model and tool releases and ethical push. October of 2025, brought forth a series of significant announcements within the artificial intelligence landscape, encompassing the release of new models, innovative tools, and expanded capabilities. Open-source initiatives propelled the boundaries of machine learning, introducing foundation models that exhibited enhanced reasoning skills, improved context comprehension, and faster processing speeds. Leading companies and research institutions unveiled sophisticated systems capable of processing extended contexts, maintaining coherence across intricate reasoning sequences, generating code with greater reliability, and interacting with multiple sensory inputs simultaneously. The relentless pace of development is evident. What was considered unattainable merely 2 years ago is now commonplace, and what appears routine today will likely be superseded within 2 years. This acceleration is tangible, measurable, and shows no signs of abating. Concurrently with these technical advancements, global forums witnessed the launch of initiatives aimed at harmonizing AI development with human values. These efforts, supported by both researchers and policymakers, underscore a consistent theme. AI possesses immense power. Its development is accelerating, and it is imperative that we ensure its alignment with our genuine aspirations, not merely our perceived desires, particularly when the consequences become tangible. The pertinent question transcends what AI is capable of doing. It delves into what it ought to do, and crucially, who holds the authority to make that determination. These are not abstract philosophical inquiries, but rather urgent practical considerations. As AI systems grow more sophisticated, autonomous, and integrated into critical infrastructure, the stakes invariably increase. An error in medical diagnostics can have fatal consequences. A malfunction in traffic control systems can lead to accidents. A miscalculation in astronomical detection could leave us vulnerable to unforeseen celestial hazards. Within astronomy, AI is already an integral component of data processing pipelines. This is not a hypothetical scenario, but current operational practice. Automated anomaly detection systems meticulously scan survey images, actively searching for transient astronomical events. Machine learning algorithms are employed to classify celestial objects, differentiating asteroids from stars, comets from galaxies, and supernovae from variable stars. These classifications are executed within milliseconds, a task that would require a human observer minutes or even hours to complete. Algorithms also refine orbital calculations by processing sets of positional measurements to determine trajectories. They predict future positions, estimate uncertainties, and flag objects whose paths intersect with Earth's orbit, thereby identifying potential hazards, objects that might pose collision risks, and those requiring further observation or addition to watch lists. The sheer volume of astronomical data generated exceeds human capacity for manual processing. Modern wide-field surveys produce terabytes of data nightly, with each image containing millions of celestial sources. Every source necessitates measurement, cataloging, and cross-referencing with existing databases. Transient events, characterized by their appearance, disappearance, or fluctuation in brightness, must be identified and flagged. The Vera C. Rubin Observatory, upon its full operational status, will image the entire observable sky every few nights, detecting billions of objects, tens of thousands of which will exhibit motion, change, or transience. No human team could manage such a data deluge. AI is essential for sifting through this information to discern signals amidst the noise. Without AI, contemporary astronomy would be overwhelmed by its own success, submerged by the immense quantity of data streaming in from telescopes each night. However, AI is not infallible and is prone to errors. It may erroneously flag false positives, objects that appear to be hazards but are not. For instance, A cosmic ray striking a detector can create a bright streak that the AI interprets as a fast-moving object, subsequently marking it as a potential asteroid. Subsequent observations would reveal no such object, confirming it as an artifact, a glitch, or a phantom. Alternatively, the AI might misclassify an object. A distant supernova that brightens gradually might have a light curve resembling that of a variable star, leading the AI to assign it to the incorrect category. Days might pass before a human identifies the error and reclassifies it, by which time the optimal observation window will have closed, resulting in the loss of critical data. Moreover, AI can miss genuine signals, particularly if they are unusual or deviate from its training data. Machine learning systems learn by example. Exposing the system to thousands of asteroids teaches it their characteristic appearance. Similarly, training it on thousands of comets instills an understanding of their typical features. However, the system may struggle when encountering an object with properties that fall outside the parameters of its training. In such cases, it might categorize the anomaly as noise, an artifact, or something to be disregarded, or it may assign it to the wrong category, sending it down an inappropriate analytical pathway. In either event, the signal is lost. AI systems can also perpetuate biases. If the training dataset is skewed towards specific types of objects, the AI will exhibit a corresponding bias. For example, if the majority of training data consists of objects identified by optical surveys in particular sky regions at specific times of year or under certain observing conditions, the AI learns this pattern. It learns that asteroids typically fall within certain brightness ranges, possess particular colors, and exhibit specific motion rates. Consequently, an object that deviates from this established pattern, perhaps it is darker than usual, has a lower albedo, or moves faster or slower than expected, or arrives from an unexpected direction, may not be recognized by an AI trained on a biased sample. It could be filtered out, effectively catching only what it was trained to detect and overlooking everything else. An additional challenge is the noise flood problem. As AI becomes more adept at identifying anomalies, it generates a greater number of alerts. While this might seem beneficial, promising enhanced coverage and fewer missed objects, it also necessitates more follow-up observations. This, in turn, demands more telescope time, human effort, and resources. Telescopes are expensive, with time on major observatories costing thousands of dollars per hour. It is impractical to follow up on every alert, requiring prioritization to determine which objects warrant the investment and which do not. If the false positive rate is excessively high, the system can become overwhelmed, leading astronomers to spend their time pursuing phantom threats and potentially missing genuine dangers. Striking a balance between sensitivity, the ability to detect real signals, and specificity, the ability to reject false signals, is inherently difficult. While both should ideally be high, a practical trade-off exists. Increasing sensitivity captures more true objects, but also more false positives. Enhancing specificity reduces false positives, but risks overlooking genuine signals. The optimal equilibrium, where most real threats are identified without generating excessive false alarms, is narrow and subject to constant shifts. It is influenced by data quality, observing conditions, and the characteristics of the targets being sought, requiring continuous fine-tuning, feedback, and human oversight. Consider a hypothetical scenario. An AI analyzing comet brightness data detects an unusual spike in R2's light curve. The comet had been exhibiting a steady increase in brightness since its discovery, consistent with rising solar heating as it approached the sun. Then, on October 15th, its brightness abruptly surged by approximately half a magnitude, a sharp, sudden change, contrary to the gradual alterations predicted by existing models. While it resembles an outburst, the timing is peculiar, deviating from the pattern of previous outbursts that occurred near perihelion when solar heating was maximal. This event, however, is happening weeks later as the comet recedes from the Sun. This raises questions. Is this observation real? Is it an instrumental artifact, perhaps due to a telescope tracking error, fluctuating atmospheric conditions, or an incorrect calibration? Or could it signify something unexpected, a physical phenomenon occurring within the comet, such as fragment ejection, a collision with a meteoroid, or the sudden release of volatile compounds? The AI cannot ascertain this. It lacks an understanding of physics or comet behavior models, merely comparing the data to patterns it has previously encountered. Because this specific pattern is unusual, it flags the anomaly and forwards it to a human observer. The human astronomer receives the alert, one among dozens. Upon examining the data, she notes the spike and checks other instruments to see if R2 has been observed recently by any other sources, seeking independent measurements that confirm the brightness change. A search of databases yields no corroborating evidence. The spike appears in only one dataset, which is cause for suspicion, as artifacts often manifest in single datasets, whereas real events are typically observed by multiple instruments unless the timing was coincidental, with only one telescope observing at the opportune moment. She reviews the observing log for any issues that night, such as telescope problems, detector malfunctions, or adverse weather. The log indicates scattered clouds and variable seeing, but nothing out of the ordinary. Examining images taken before and after the spike, she finds the comet appearing normal, with no discernible structural changes, new fragments, or dramatic brightening in subsequent observations. The spike appears to have been transient, if indeed it was real. It could have been noise or a brief, real event, too short-lived to be confirmed by other observers. She makes a decision. The evidence is ambiguous, and the spike is likely an artifact. Without confirmation or additional data, issuing an alert would be premature, potentially consuming resources, triggering unnecessary follow-up observations, mobilizing other astronomers, and ultimately wasting everyone's time if the spike proves to be nothing. She opts not to issue an alert. The anomaly is logged in the database, marked as unconfirmed and essentially forgotten. She proceeds to the next alert. The system continues its operations, but what if the spike was genuine? What if it indicated fragmentation, with pieces now diverging from the parent trajectory? The human decision, made under conditions of uncertainty and incomplete data, might have overlooked something significant. Fragments take time to separate. In the initial hours or days, they remain close to the parent body, making them difficult to resolve even with high-resolution imaging. By the time they have separated sufficiently to be observed as distinct objects, they may have diverged enough to pose separate threats. The AI, which had detected the anomaly, is thus disregarded, not due to human negligence, but because the astronomer followed established protocols, evaluated the available evidence, and made a reasonable judgment. However, reasonable calls made amidst uncertainty can sometimes prove incorrect. Over time, humans may develop a distrust of AI alerts due to the prevalence of false positives. This phenomenon, known as alert fatigue, is well documented in fields such as medical diagnostics, aviation safety, nuclear power plant operations, and now, astronomy. When alarms sound frequently without subsequent validation, individuals tend to become less responsive, tuning out the signals and developing heuristics to filter the perceived noise. For instance, A human might decide to act only on alerts with confidence scores above 90%, or to follow up only if multiple instruments flag the same object, or to deprioritize alerts from older telescopes with known calibration issues. While these heuristics are rational and serve to save time and focus resources on more promising targets, they can inadvertently filter out genuine signals. The actual threat, the one that truly matters, might possess a confidence score of 85%, be flagged by only a single instrument due to fortunate timing, or originate from an older telescope that, despite its age, has detected something real. In such instances, the alert might be dismissed as noise. The pattern recognition that aids humans in managing information overload can also obscure genuine anomalies. This presents the core challenge of human-AI collaboration. Neither party is perfect. AI is characterized by speed, but lacks understanding. It processes vast quantities of data in seconds, identifying patterns that would take humans hours to discern. It does not experience fatigue or loss of focus, but lacks contextual awareness and intuition, and cannot reason about the physical plausibility of an anomaly. Humans, conversely, are slow but intelligent. They understand physics, possess intuition, and can reason about causality and plausibility. However, their capabilities are constrained by attention spans, fatigue, and cognitive biases, limiting them to examining only a fraction of the data and potentially missing events outside their immediate focus. The most effective system arises from their complementary strengths. AI handles the data volume, flagging anything unusual for human evaluation, while humans apply context and intuition to discern what is real from what is noise. This necessitates trust, calibration, and feedback loops. Humans must trust that the AI is not overlooking critical signals, and the AI must be calibrated to generate informative rather than overwhelming alerts. Feedback mechanisms are crucial, allowing humans to inform the AI of its correct or incorrect assessments, thereby enabling the system to learn and improve. Furthermore, it requires sustained human vigilance to avoid complacency and the assumption that the AI will detect everything. The moment humans begin to perceive AI as infallible, as a perfect detector incapable of error, the system becomes dangerous. This is because AI is not infallible. It is a tool, powerful yet limited, requiring human oversight for optimal functioning. The true danger lies not in AI's potential for failure, but in humanity's propensity to trust it excessively and cease paying attention. When attention wanes, undetected issues begin to accumulate. Detection is no longer solely a matter of hardware, of constructing larger telescopes with superior mirrors and more sensitive detectors. It is intrinsically linked to software, algorithms, decision trees, neural networks, and statistical thresholds. It involves the rules we establish to differentiate signal from noise, the models we develop to predict trajectories, and the pipelines we create for data processing. All these elements are human constructs, trained on data selected by humans and deployed within contexts defined by humans. The biases, the gaps, and the blind spots are therefore human creations, choices, whether deliberate or unconscious, embedded within the systems we build. While AI can enhance our observational reach, it cannot resolve the fundamental challenge. We are seeking patterns in a universe indifferent to our success. The universe does not prioritize our detection efforts. It does not simplify our task. Objects appear from inconvenient angles, at inopportune times, and possess characteristics that do not conform to our training data. They may be obscured by the sun's glare, arrive during adverse weather conditions, or fragment unpredictably. Our detection systems, both human and artificial, must adapt to this reality or face failure. The challenge extends beyond merely developing superior tools. It encompasses fostering enhanced collaboration between these tools and the individuals who utilize them. Next, we will examine another neuroscience study, this one focusing on spatial memory and aging, serving as a metaphor for the degradation of detection systems over time. This is part 14, Instrument and Sensor Degradation Metaphor, Stanford Spatial Memory and Aging. On October 3, 2025, researchers at Stanford University published their findings regarding the decline of spatial memory in aging brains. Their research focused on neurons within the hippocampus, the brain region responsible for constructing cognitive maps of the environment. These maps are not abstract constructs, but represent a tangible representation of our surroundings. These are internal blueprints of physical environments, formed from lived moments and honed through repetition. In developing creatures, these specific nerve cells activate reliably when the organism finds itself in a particular place. The activation sequence is exact, constant, and repeatable. Neuron alpha sparks when the creature is in the first corner. Neuron beta sparks when it is in the second corner. This arrangement constructs a mental layout, a neural grid reference system that allows the creature to ascertain its location and determine the route to its desired destination. However, in mature creatures, the nerve cells exhibit less dependable activity. Neuron alpha might activate in the first corner, or it could activate in the second corner, or it might remain silent. The mental map becomes indistinct. Different locations merge. The creature still comprehends its presence somewhere, but that somewhere lacks precision. Locomotion becomes more challenging. The creature hesitates. It retraces its steps. It makes incorrect turns. It eventually arrives at its objective, but the journey is inefficient, fraught with uncertainty, and marked by missteps that a younger creature would not experience. The investigation delved into the underlying cause of this deterioration. Certain protein molecules accumulate with advancing years, attaching to receptors at nerve junctions and diminishing their adaptability. Nerve junction adaptability is the capacity of connections between nerve cells to intensify or weaken based on encountered events. It serves as the physical foundation for acquiring knowledge and forming memories. When adaptability wanes, nerve cells lose their proficiency in updating the map, rectifying errors, and integrating novel information. The consequence is a degraded internal representation of space. The map persists, but it is outdated, imprecise, and unreliable. The creature continues to navigate, but with diminished accuracy. It commits more blunders. It requires a longer duration to locate objectives. This decline is gradual, initially subtle, yet measurable. Over time, it amplifies. The errors accumulate. The map deteriorates. This discovery extends beyond mere neuroscience. It functions as a symbol for every detection system humanity has ever conceived. Telescopic apparatuses age in precisely the same manner. Instruments commence with sharpness, accuracy, and calibration, finely tuned to detect the faintest signals, but over time, they decay. Optical alignment drifts. The reflective surfaces that concentrate starlight are supported by mechanical frameworks that expand and contract with thermal variations. Over months and years, minute shifts accumulate. The focus softens. The image diffuses. Light that ought to converge on a singular pixel disperses across several. This is referred to as the point spread function, the mathematical depiction of how a telescope renders a pinpoint light source, which broadens. The capacity for discernment diminishes. Mirrors gather dust, Even in the most sophisticated astronomical observatories, even within sealed environments, particulate matter settles on the optical surfaces. Dust disperses light, reducing the quantity that reaches the sensor. Even more problematic, some telescopes are exposed to the elements. Wind carries abrasive particles. Temperature fluctuations induce condensation. Over time, the mirror surface undergoes oxidation. The aluminum coatings applied to create reflective surfaces deteriorate. Reflectivity drops from 98% to 95%, then to 90%. Each lost percentage point signifies fewer photons captured. Fainter celestial bodies are missed. Ultimately, the mirror necessitates stripping and reapplication of the reflective coating, a procedure that consumes weeks and incurs costs of hundreds of thousands of dollars. Sensors develop imperfections. Charge-coupled devices, the silicon chips that convert photons into electrical charges, accumulate damage from cosmic radiation. High-energy particles impact the silicon lattice, dislodging atoms and generating hot pixels that register erroneous signals. Dead pixels emerge, areas where photons arrive but no signal is recorded. Noise patterns manifest, systematic errors that must be accounted for during image processing. The detector still functions, but its dynamic range contracts. Its sensitivity declines. Objects at the threshold of detection, those that produce only a handful of photons per exposure, fall below the ambient noise level. They disappear. Calibration becomes less precise. Every telescope requires regular calibration to translate raw detector readings into meaningful measurements. One directs the telescope at stars of known luminosity, records the signal, and constructs a calibration curve. However, calibration drifts. The detector's response shifts, the optical transmission varies, and the atmospheric conditions change. If recalibration is not performed frequently, measurements become unreliable. An object believed to be of magnitude 6 might actually be of magnitude 5.8 or 6.2. This uncertainty propagates. Luminosity estimations become less dependable. Orbital projections reliant on luminosity become less accurate. The margins of error expand. The images grow hazier. The detection threshold elevates. Objects that were once discernible, that previously yielded clear, confident detections, now hover at the boundary of statistical significance. Is that celestial phenomenon a comet or a random noise fluctuation? Is it a moving object or a cosmic ray impact? The ambiguity intensifies. Observers experience reduced confidence. Subsequent investigations are necessary, but telescope allocation time is limited. If every marginal detection necessitates confirmation, the system becomes encumbered. The processing queue lengthens. Objects move beyond the observational window before they can be verified. They are lost. Maintenance offers partial mitigation, but only up to a certain point. Mirrors can be cleaned. Dust can be removed through careful wiping or by being dislodged with compressed air. However, cleaning introduces risk. A scratch, a smudge, a residual film left behind can exacerbate the problem. Reapplication of reflective coating restores luminosity, but it demands the removal of the mirror, its transportation to a specialized facility, a waiting period of weeks for the process to conclude, followed by reinstallation and realignment. During this downtime, the telescope is inoperative. Observations cease. The survey is suspended. Objects that would have been detected within that interval are missed entirely. Sensors can be replaced. New charge-coupled devices, offering enhanced quantum efficiency, reduced noise, and broader dynamic range, are available, but their replacement is costly. A single detector can cost millions of dollars. Installation requires extreme precision. The detector must be cooled to cryogenic temperatures to minimize thermal noise. The cooling mechanism requires continuous upkeep. Leaks occur, pumps malfunction, systems become inactive, and even with a new detector, the rest of the optical assembly continues to age. The telescope's effectiveness is limited by its least capable element. Calibration can be repeated. In principle, recalibration should occur nightly using standard stars, verifying the 0 point and measuring atmospheric extinction. In practice, atmospheric obscuration intervenes. Schedules are delayed. Automated processing systems utilize outdated calibration files. The drift goes unnoticed until an individual investigates and realizes the measurements are inaccurate. By then, potentially weeks or months of collected data may be compromised. Orbits calculated from that data carry forward the error. Objects are misplaced. Predictions fail. However, maintenance necessitates resources, time, financial investment, and specialized knowledge. Budgets are finite. Funding bodies prioritize new undertakings over the upkeep of existing ones. Once a telescope is constructed and operational, the initial excitement subsides. The prominent news coverage moves on. The scientists who conceived it retire. The engineers who assembled it transition to other projects. The institution is left with an aging apparatus and a diminishing budget. Maintenance is deferred. Upgrades are postponed. The system deteriorates at a faster rate than it can be repaired. Entropy prevails. The research from Stanford demonstrates that even biological systems, which are self-perpetuating and constantly regenerating, still exhibit decline with age. Nerve cells lose functionality despite the brain's capacity to form new neural connections, eliminate unused pathways, and reconfigure neural networks. The hippocampus is among the limited brain regions where new nerve cells are generated throughout life. Neurogenesis continues into advanced age. Yet, even with this regenerative capability, spatial memory diminishes. The newly formed nerve cells do not fully compensate for the accumulated damage. Neural connections weaken, proteins accumulate, and internal maps become unreliable. The rate of degradation is slower than it would be without regeneration, but it is still unavoidable. Our astronomical instruments lack this inherent advantage. They are not self-regenerating. They do not replenish themselves. Once damage occurs, it persists until an intervention is made. Such interventions are time-consuming, expensive, and often incomplete. A mirror cleaned today will gather dust tomorrow. A sensor replaced today will develop hot pixels next year. A calibration performed today will drift next month. The degradation is relentless. The pace is more rapid than in biological systems because there is no integrated repair mechanism. And as the instruments degrade, we miss crucial observations. The celestial object R2 serves as an illustrative example of how detection failures occur. The comet was identified late because it was situated in a geometric blind spot, obscured by the sun's intense glare. However, blind spots are not exclusively geometric. At times, they are instrumental. A faint comet, at the limit of detection, might be visible to a new telescope with a recently recoded mirror and an unblemished sensor. The same comet, observed months later with the identical telescope after dust accumulation and sensor degradation, might be imperceptible. The object itself has not changed. The telescope has. Consequently, due to the telescope's diminished performance, the detection fails. The identical celestial body, observed using the same methodology, yields divergent results depending on the instrument's condition. This is not a hypothetical scenario. It is a recurring issue. Survey telescopes detect fewer objects in their later operational years compared to their earlier years. Although the celestial sphere remains unchanged, this decline is attributed to aging hardware, deteriorating optics, and sensor malfunctions. If this degradation is not accounted for, if instruments are not regularly tested and recalibrated, and if their performance over time is not meticulously tracked, we begin to overlook objects that were previously detectable. We fail to realize we are missing them because they never appear in the collected data. They exist as spectral apparitions, unseen, undetected, and unknown. Furthermore, there is data fatigue, a distinct form of degradation. Telescopes generate colossal volumes of information. Modern wide-field surveys produce petabytes of data annually. Each captured image contains millions of pixels, and each pixel represents a measurement. Processing this data necessitates sophisticated software pipelines. These automated systems identify celestial sources, ascertain their positions, calculate their magnitudes, cross-reference them with existing catalogs, and flag anomalies. These pipelines operate continuously, ingesting new data and outputting results. However, as the volume of data escalates, the processing pipelines experience strain. Processing durations extend. Queues form, leading to data backlogs. An image captured tonight might not be processed until tomorrow or even the following week. By the time an anomaly is flagged, and a human reviews it to determine if follow-up observation is required, the celestial object has moved considerably. The window for observation closes. We lose the opportunity to confirm its identity, refine its orbital trajectory, or assess any associated risks. Data storage presents another impediment. Petascale data requires extensive infrastructure, including hard drives, servers, cooling systems, and redundancy measures for backups. All of these components incur significant financial costs. When budgets are tightened, data storage capacity is often reduced. Older datasets are archived to slower storage media, such as tape drives, which can take hours to access. If there is a need to reprocess historical images or search for a faint object that was initially overlooked, one must endure a waiting period. A request is submitted, followed by a wait for the tape to be loaded, the data to be transferred, and the processing to be completed. Days pass, and by then, the object of interest may have long since moved on. Vigilance necessitates continuous maintenance, not only of hardware, but also of software, operational procedures, and accumulated institutional knowledge. Software is prone to bugs. Processing pipelines incorporate inherent assumptions. A threshold established 5 years ago may no longer be appropriate. The celestial environment has changed. Light pollution has increased. Satellite constellations have multiplied. The number of streaks and flares within each image has dramatically escalated. The pipeline flags these as anomalies, and the queue becomes inundated with false positives, obscuring genuine anomalies. Adjusting the detection threshold is not a straightforward task. Modifying it excessively could lead to the omission of genuine celestial objects, while setting it too low would perpetuate the influx of false positives. An individual must meticulously monitor the pipeline, fine-tune its parameters, and rigorously test the resulting outputs. This requires expertise, experience, and a deep understanding of the system's historical context. Astronomers retire, and engineers move on. The individuals who designed the system, who comprehend its intricacies, who are aware of its blind spots, and who recall the rationale behind specific design decisions, eventually depart. While documentation offers assistance, it is never entirely comprehensive. Subtle nuances tend to be lost. New personnel join the team. They learn the system, but they do not possess the intimate familiarity gained through years of direct engagement. Mistakes inevitably occur. A parameter is altered without fully grasping its downstream implications. A calibration file is updated erroneously. An assumption is made that was previously examined and dismissed. The new team lacks the historical context. They inadvertently repeat past errors. The system gradually deviates from its optimal performance. Detection rates decline. This goes unnoticed until someone conducts a retrospective analysis and discovers that the telescope is failing to detect objects it should be capable of observing. The parallel with aging brains is exact. Both systems begin with high precision, degrade incrementally, lose sensitivity, and miss signals. Both necessitate proactive maintenance to decelerate the decline. Ultimately, both systems fail despite our most diligent efforts. The solution remains consistent: refurbish, recalibrate, upgrade, and replace aging components with new ones. Train the subsequent generation of experts. Document everything thoroughly. Cultivate institutional memory. Resist entropy at every level, acknowledging that permanent victory is unattainable, but hoping to postpone the inevitable for a duration sufficient to make a meaningful impact. Researchers at Stanford demonstrated that inhibiting age-related proteins in mice led to a partial restoration of spatial memory function. This intervention did not rejuvenate the older mice. Rather, it mitigated their aging process. It slowed the rate of decline. It bought valuable time. This is precisely what maintenance achieves for telescopes. It does not restore them to their original factory condition, but rather decelerates their degradation. It effectively buys time to detect the next R2, the next unexpected celestial visitor, the next object concealed within the glare or residing at the edge of our observational capabilities. Time is the most critical resource. When systems falter, when detection lapses occur, and when degradation triumphs, we lose precious time. And losing time equates to forfeiting the opportunity to observe what is approaching before it arrives. In the upcoming segment, we will conclude this discussion. We will address what lies ahead, what you should monitor, what you should advocate for, and how all of this connects to Apophis, the asteroid known to be approaching in the year 2029. Part 15, Global Synopsis, What to Observe Next, and Mission Roadmap. If R2 serves as a cautionary signal, here is our path forward. The comet will make its closest approach on October 20th, 2025, at a distance of 0.26 astronomical units, which is equivalent to 8 days. Between now and then, the following actions are imperative. Firstly, ephemeris updates. Continuously track the trajectory. Refine the orbital path. Monitor for any perturbations. Outgassing generates non-gravitational forces. If the comet experiences another outburst, if it vents material asymmetrically, its trajectory will shift. The alteration may not be substantial, but it could be significant enough. Maintain continuous measurement. Continue refining. Do not assume the current orbital solution is definitive. Secondly, spectroscopy and radar observations. It is crucial to ascertain the composition of R2. Spectroscopy provides information about the gases vented, the molecules present, and the composition of the comet's coma. Radar, provided the comet approaches sufficiently close and we direct the appropriate instruments towards it, can resolve the nucleus, measure its size, detect its rotation, and potentially reveal its internal structure. This pursuit extends beyond mere scientific curiosity. The comet's composition directly influences its behavior. Nuclei rich in volatile substances are more prone to outbursts. Structural integrity affects the risk of fragmentation. If the nucleus is a loosely aggregated collection of debris, Held together by weak gravitational forces, it might disintegrate. Conversely, if it is a solid monolithic body, it will remain intact. We need to know which scenario applies. Thirdly, high-resolution imaging. Efforts should be made to resolve the nucleus and detect any fragments. If R2 has fragmented, if pieces are dispersing, it is imperative to identify them now while there is still adequate time to track their trajectories. Fragments diverge slowly initially. The earlier we detect them, the more effectively we can predict their future paths. Fourthly, monitoring of dust and debris. Investigations should focus on identifying trails, observing ejection events, and detecting meteoroid activity. Earth-based meteor detection cameras can identify particles entering the atmosphere. Satellite sensors can quantify micrometeoroid flux. If R2 is shedding debris, and if Earth is traversing a debris stream, we require advance notification. Even a few hours of warning are sufficient to place satellites into a protective mode, orienting their solar panels edge-on to minimize their cross-sectional area. Fifthly, spacecraft hazard modeling. The International Space Station orbits at an altitude of approximately 400 kilometers. Satellites occupy various altitudes, ranging from low Earth orbit to geostationary orbit at 36,000 kilometers. All of these are potential targets. A dense meteoroid stream amplifies collision risk. While the risk remains low, low is a relative term. If the background flux is 1 particle per million cubic kilometers per hour, and a debris stream elevates this to 10 particles per million cubic kilometers per hour, that represents a 10-fold increase. Small numbers, multiplied by vast volumes and extended exposure durations, accumulate. Modeling the flux allows for risk estimation and the preparation of contingency plans. Now, concerning policy and systems, what should we demand from the institutions tasked with our protection? Firstly, invest in solar flank surveillance. The majority of our telescopes are directed away from the sun. This is a natural inclination, as the sun's intense brightness can blind sensors. However, objects approaching from the sun's direction remain invisible until they emerge from its glare. We require space-based telescopes strategically positioned to observe the sun. These instruments, essentially solar wards, are capable of detecting comets and asteroids within the sun's intense radiation. The SOHO SWAN instrument has already demonstrated the efficacy of this approach. We need additional instruments of a similar nature, specifically dedicated to comet detection and covering a broader spectrum of observation. Secondly, establish real-time public data pipelines. Transparency effectively mitigates the void created by speculation and conspiracy theories. When observational data is published immediately, when orbital solutions are updated in real time, and when uncertainties are communicated with clarity, public trust is enhanced. Individuals do not need to resort to conjecture when the relevant data is readily accessible. The Minor Planet Center and JPL already provide some of this information, but their interfaces are highly technical. We need publicly accessible dashboards, visualizations, and summaries presented in plain language. Make the data comprehensible and easy to utilize. Thirdly, foster international coordination. Telescopes are distributed globally, each operating within different time zones, offering varying sky coverage, and possessing distinct observational capabilities. A network coordinated in real time can facilitate continuous tracking of celestial objects. When one telescope loses sight of an object as it descends below the horizon, another can seamlessly pick up the observation. Alert protocols need to be standardized. If one observatory detects a potential hazard, how rapidly is this information disseminated to other observatories? How quickly does it reach decision makers? Minutes are critical. Hours are critical. Days are critical. To draw a contrast, let us consider Apophis. Asteroid 9992. Apophis, with a diameter of approximately 340 meters, will pass closer than geostationary satellites on April 13, 2029. This is less than 4 years away. We have been aware of Apophis since 2004. We have tracked it for 21 years. We know its orbit with remarkable precision. We know its exact position on April 13, 2029, down to the kilometer. We are certain it will not impact Earth. We know it will pass at an estimated distance of 31,000 kilometers, closer than some satellites, but still within a safe margin. We have ample time to prepare, to position observational instruments, and to study it during its close approach. Apophis represents the predictable scenario, the one we foresaw, the one we can observe in slow motion. R2, conversely, is the opposite. Unpredictable, detected late, with an uncertain orbit, unknown composition, and the potential for fragmentation. R2 is the type of event that causes concern for risk analysts, not because it poses an impact threat, but because it was nearly missed. And there are other similar objects, others that we have not yet observed, others that we will not detect until it is too late. The fundamental difference between Apophis and R2 is time. Apophis afforded us decades of observation. R2 provided us with mere weeks. Time is the most crucial resource in cosmic defense. It is the time required for observation, for trajectory refinement, for evaluating potential courses of action, and for implementing necessary measures. When time runs out, options vanish. All that remains is observation, hoping, and praying that the calculations hold true, that the uncertainties do not shift unfavorably, and that any fragments do not deviate into Earth-crossing trajectories. Large, predictable objects command attention. Apophis will be subjected to exhaustive scientific scrutiny. Every telescope will be directed towards it. Every radar system will attempt to ping it. We will acquire more knowledge about asteroids during a single flyby than we have in decades of distant observations. This is a positive development. The real danger arises from the celestial bodies we fail to anticipate. These are the small, swift, unforeseen entities, the true unknowns, the ones that lurk in plain sight, appearing from unexpected directions, suddenly illuminated after we've averted our gaze. These are the events that will invariably catch us unprepared. The cosmos harbors no malevolent intent. It neither seeks our destruction nor offers salvation. It operates with utter indifference. Celestial objects traverse the void governed by the immutable laws of gravity and momentum. Occasionally, their trajectories intersect with ours. Most veer away, while a few collide. This occurrence is a matter of statistical probability, appearing random over brief spans, but becoming predictable across extended periods. We are fortunate to exist within a fleeting epoch where cosmic impacts are sufficiently infrequent to permit the flourishing of civilization, yet recurrent enough to necessitate constant vigilance. The colossal impactor responsible for the extinction of the dinosaurs occurred 66 million years ago. It measured 10 kilometers in diameter, hurtled at 20 kilometers per second, and unleashed an energy comparable to billions of nuclear detonations. This impact carved a chasm 200 kilometers wide, propelled ejecta into the stratosphere, plunged the world into darkness, and marked the end of an age. Such an event could transfigure again. Not imminently, not in our foreseeable futures, but eventually. The paramount concern is whether we will possess the foresight to detect it, whether we will have adequate time to intervene, whether we will have established the necessary infrastructure, developed the requisite technologies, trained the appropriate personnel, and forged the collaborative alliances to orchestrate a defense? Or will we, like the dinosaurs, remain oblivious until the heavens ignite? The object designated R2 will not be that cataclysmic event. Its size, distance, and meticulously tracked trajectory preclude such a scenario. However, it serves as a crucial test, a trial of our detection capabilities, our communication networks, and our capacity to confront uncertainty with reasoned action rather than succumbing to panic. To date, we are meeting this challenge. The comet is under continuous observation. Its orbital path is being precisely calculated. The associated risks are being clearly communicated. There is no widespread alarm, nor is any warranted. Nevertheless, our attention should be directed not towards the spectacle or sensational headlines, nor towards unfounded theories, doomsayers, or profiteers of hysteria. Instead, we must focus on the deficiencies, the blind spots, the lapses in detection, the bureaucratic entanglements, and the elements we overlook due to misdirected focus, mistimed observation, or inadequate instrumentation. These are the genuine lessons. These are the matters of consequence. Observe the heavens. Advocate for enhanced observational systems. Scrutinize prevailing narratives. Cultivate intellectual curiosity. Maintain a healthy skepticism. The universe teems with both marvels and perils. Most of the time, the wonders can be appreciated without apprehension. However, the dangers do not herald their arrival. They do not seek permission. They simply manifest. And when they do, the sole bulwark separating us from oblivion is the efficacy of our detection mechanisms and the swiftness of our response. 8 days remain until its closest proximity. R2 is approaching. We are observing. The statistical projections indicate our safety, but numbers do not equate to certainty. Their probabilistic representations, cloaked in equations, can occasionally defy expectations. This is precisely why we observe. This is why we calculate. This is why we construct telescopes, train astronomers, fund observational programs, and foster international cooperation. Because the alternative is ignorance, and ignorance is a far greater threat than the celestial bodies themselves. The cosmos is not a void. It is a dynamic expanse populated with debris, fragments, transient visitors, and celestial wanderers. The majority traverse our celestial neighborhood harmlessly. Some do not. R2 serves as a poignant reminder that our cosmic environment is far from tranquil, that traffic is a constant reality, that the risk, while diminished, is never eradicated, and that vigilance, rather than being a symptom of paranoia, is an essential component of survival. Continue your observations.